Most modern aircraft use alternating current, or AC, in their primary electrical systems. The AC is supplied by an alternator or alternators. Alternators are often referred to as AC generators, and this is the name that we will use. We will begin this lesson by reviewing the operation of a simple AC generator. We will then go on to look at polyphase or multi-phase AC generation. In a DC generator, the rotating part is always the armature. In an AC generator, this is not necessarily true. There are two types of AC generator. They are the rotating armature type and the rotating field type. The rotating armature AC generator is similar in construction to a DC generator in that the armature rotates in a stationary magnetic field. As it does so, an EMF is induced into it, and this EMF, rather than being converted to DC, as it is in the commutator of a DC machine, is taken from the rotating assembly as AC through slip rings. Rotating armature AC generators suffer from a number of disadvantages. The rotating coils are heavy and centrifugal forces are high. Efficient insulation of the rotating coils is difficult. The resistance across the brushes to the slip rings is high, and the rotating armature coils are difficult to cool. For these reasons, the rotating armature is only used in very small output AC generators and is not generally used for supplying aircraft AC systems. Most AC generators are designed with a rotating field and a stationary armature, in the same way that DC alternators are constructed, but without the rectifier. The rotating part of the generator is known as the rotor, and the stationary part the stator. The field can be energized either by a permanent magnet or by DC from a separate source. One advantage of a rotating field AC generator is that only a low current is fed through slip rings to the field windings. The output is taken from the stationary armature windings, which means that problems associated with arcing from the brush gear are greatly reduced. The stator windings or coils are directly opposite each other and are connected in series to supply the output. The rotor consists of two poles of opposite polarity. The maximum output current from an AC generator depends on the amount of heat which can be absorbed by the armature. The armature windings, in common with all conductors, have some resistance. The power lost in the armature is this resistance multiplied by the armature current squared. This power loss heats up the conductors and can, in extreme cases, destroy the insulation of the windings. For this reason, AC generators are rated in terms of this armature current as well as by their voltage output. Thus, every AC generator is rated in voltamps or kilovoltamps. You will recall that this is the apparent power being felt by the armature. Polyphase or multi-phase AC generators have two or more sets of single-phase armature windings, commonly known as phases, symmetrically spaced around the stator. The most common polyphase AC generator has three sets of armature windings. It is known as a three-phase generator and has become the standard AC generation system for aircraft. The phase windings are named A, B, and C. They are mechanically arranged to be at 120 degrees to each other, in the sequence A, B, C. The currents and voltages generated in this type of machine will have the same frequency, but be out of phase with each other by 120 degrees. It can be seen that A phase reaches a peak going positive 120 degrees before B phase reaches a peak going positive. B phase, in turn, peaks 120 degrees before C phase reaches a peak going positive. This gives the phase sequence ABC. The peak values of the voltages induced in the three single-phase windings of the three-phase alternator are therefore 120 degrees displaced from each other. The three phases are independent of each other. A system using three-phase generators has a number of advantages over a system using single-phase machines. Because the generators are effectively three single-phase generators on the same shaft, they have a greater power-to-weight ratio. Three-phase AC motors are very simple and efficient, and for reasons beyond the scope of this course, three-phase generators are easier to connect in parallel than single-phase devices. Although we have said that the three phases are independent of each other, it is normal to connect their outputs together. The outputs can be connected by either the star or delta method. A star-connected three-phase AC generator has the three phases joined at one end to form a connection known as the neutral point. The connections at the opposite end of the phase windings from the neutral are called the line connections. The neutral point is normally grounded and used as the earth return in modern aircraft. It will carry any out-of-balance current between the phase loads. A voltmeter, measuring the potential difference between the neutral and a line lead, would read the individual phase voltage. The potential difference between two line connections is known as the line voltage. In this type of AC generator, the phase voltage and line voltage are different. Because phase voltage is measured across one phase, whereas line voltage is measured across two phases and is the vector sum of the two. The line voltage in a three-phase system can be found by multiplying the phase voltage by the square root of 3, or 1.73. The phase voltage of a typical aircraft supply system would be 115 volts. So from the formula, we can work out that the line voltage is 115 multiplied by root 3, which is approximately 200 volts. The frequency used on aircraft is normally 400 Hz, so a modern aircraft power supply would be 115/200 volts, 400 Hz, three-phase. The Greek letter phi is often used to represent phase. While the voltages of line and phase differ in the star-connected system, because the windings form only one path for current flow between phases, the current flowing in the lines will be the same as the current flowing in the phase windings. Thus, line current equals phase current. In a delta-connected AC generator, the ends of the three phases are joined together to form a closed mesh, and the loads are connected in a similar fashion. Because the potential measured across the phase is measured between two lines, the line voltage and the phase voltage are the same. However, because of the way the phases are connected, the line current will always be shared between the phases. And in this case, the line current will be root 3 times the phase current. This type of connection is not normally used in aircraft electrical power systems, because it cannot cope with unbalanced loads, as there is no neutral point. However, it may be used for rotational speed sensing equipment, such as in engine RPM indicating systems. That is the end of the lesson. Here are the main points that you should take from it. Most aircraft AC generators have their field windings on the rotor and their armature windings on the stator. AC generators are rated in voltamps or kilovoltamps. Aircraft AC generators are usually 115/200 volt, 400 Hz, three-phase star-connected machines. The three phases are separated by 120 degrees. In a star-connected generator, the line voltage is equal to √3 or 1.73 times the phase voltage. The line current is the same as the phase current. In a delta-connected machine, the line voltage is the phase voltage, but the line current is √3 times the phase current.